Hi there, class. Welcome to lesson 13.2, Angles of Rotation. This lesson has a warm-up, so please pause the video now and complete the warm-up. Well, thanks for trying the warm-up. In each of the first four questions, you needed to find the supplement for the given angle. And remember that supplements are two angles that add up to 180 degrees. So each of these answers could be found just by subtracting the angle that was given from 180 degrees. In number 5, in order to find the three trig ratios, sine, cosine, and tangent, you needed to first find the missing side. Well, the missing side happened to be a leg. And so with Pythagorean's theorem and using simplest radical form, I was able to find that the other leg was 4 square roots of 5. And so then comparing the sides in ratio, the sine ratio is the opposite to the hypotenuse, and that turned out to be 2/3. The cosine, adjacent to hypotenuse, that when I reduced it, turned out to be the square root of 5/3. And finally the tangent. Once I rationalized the denominator and did some reducing, the tangent, which is the opposite over the adjacent, turned out to be 2 square root of 5/5. So here's what we have in store for this lesson. Our first learning goal is we are going to draw angles in standard position, including negative angles and angles greater than 360 degrees. Next, we're going to be, if we're given an angle in standard position, we're going to be finding coterminal and reference angles. And finally, we're going to determine the value of the trigonometric functions for an angle in standard position, specifically corresponding to a point in the coordinate plane. So far we have been limited with our trig ratios to just acute angles, those that could be the non-right angle in a right triangle, which would of course both be acute angles. So if we want to move beyond acute angles for our domain, we want to be looking at angles of all measures. And so by looking at angles that are formed by rotations in the coordinate plane, we're able to do that. So an angle is in what we call standard position when its vertex is at the origin and one ray is on the positive x-axis. So this angle, for instance, is in standard position. It is an acute angle because we can tell it's less than 90 degrees. It has one of its sides on the positive x-axis here, and the other, the vertex is at the origin, and the other side is here. And that would be called a standard position angle. So the side that's actually on the x-axis is actually called the initial side. And that other ray is called the terminal side of the angle. So this one right here would be the initial, sitting on the x-axis, and this would be the terminal side. And here are some other angles in standard position in this table here. This one's a 135-degree angle. You see the initial side begins on the x-axis going in the positive direction, and the terminal side, because it's a 135-degree angle, ended up in the second quadrant. After 90-degree turn takes you to the positive y-axis, and then continuing on past that to make 135 degrees. So these angles are actually formed by rotating the terminal side. If that terminal side is rotated counterclockwise, then the angle of rotation is said to be positive. Here's an example of a positive angle of rotation, because the initial side starts on the x-axis and the terminal side is then rotated in a counterclockwise direction. So that would be a positive angle of rotation. If that terminal side is rotated clockwise instead, then the angle of rotation is said to be negative. And here is an example of a negative angle of rotation. Started at the initial side and was rotated in a clockwise direction, 45 degrees, and so you see that angle of rotation is classified as a negative 45-degree angle. And finally, the terminal side can be rotated more than 360 degrees. So if you make more than one time around the circle, you can just kind of continue on, and so you can now include angles that are beyond 90 degrees. So we can go, even past 360 degrees, and we can even go in the negative direction. So let's go ahead and turn the page. So our first learning goal is to draw angles in standard position. So if we're going to draw angles in standard position, we need to have sort of a little coordinate plane. And so for each of these, we're just going to sketch just a little set of X and Y axes. So you can either do them all right now if you want to, or I guess just do them as we get to the question. So if I wanted to draw an angle that was 320 degrees, every one of these angles is going to start with one of its sides right there on the x-axis. So I'm going to start with my initial side right there. And then I know if I want it to rotate 320 degrees, well, first of all, if I went through the first quadrant here, that would be 90 degrees. And then there's 180 degrees if I got to the other side of the x-axis. So I've gone 180. Now another 90 degrees would get me to 270 degrees. And then if I wanted to go 320, that means I would have to go 50 more degrees. So I could kind of estimate that to be about just a little more than halfway, because that's another 90-degree angle down there. So I went about just past halfway. And that's where my angle is going to end. And so then I'll draw in the terminal side here. And basically this part, my orange highlighted part, that kind of just shows the direction that I'm going, so that the person seeing my angle knows that I actually went in a positive direction. And so then I usually will label it right on the drawing that that was 320 degrees. So let's try another one. This time I have a negative 110 degrees. So I'm going to start off with my initial side on the x-axis, and this time I'm going to have to go clockwise. So I'm going to be traveling in a clockwise direction. So this way there's 90 degrees. So if I've already gone 90, then I have 20 more degrees to go. So I estimate this to be about 20 degrees, right about there. And I'm going to draw in the other side of the angle, and there it is. And then I'm going to label right on the angle that I went negative 110 degrees. Okay, so this next one, 990 degrees. Wow, that's a big angle. So if I start off on this initial side here, and I'm going to go 990 degrees, that means I'm going to go more than one time around. So if I started off and I started going around this circle, I would go, let's see, one time around. Okay, so there's 360 degrees, but I have to keep going. So if I went around another time, another 360 degrees, I still only gone 720 degrees. And so now I know if I think about 990 and I subtracted 720 that I've already gone by going 2 times around, that leaves me with another 270 degrees to go. So there's 90, there's 180, and there down here at the bottom, that's 270 degrees. So that terminal side is going to be right here on the y-axis, but I actually had to travel a full 990 degrees in the counterclockwise direction to get there. So really it doesn't look any different than if I had just gone 270 degrees counterclockwise, or even negative 90 degrees, so in the clockwise direction. But kind of showing those little loops there, I can see that I went 2 full times around and then another 270 degrees. So go ahead and pause the video and let's set these two to be you try questions. You try question for D, go 1020 degrees, and then you try for E, negative 300 degrees. So on that 120 degree angle, you went almost 3 times around, just a little shy of that. 2 full times and then another 300 degrees. And then with a negative 300 degrees, not quite 1 full time around, but in the clockwise direction this time. So coterminal angles are angles that would be in the same standard position with the same terminal side. Or they're in the angles in standard position with the same terminal side. So like for instance, if let's say you went, we looked at this last one that you graphed, this one that was negative 300 degrees. Well, going negative 300 degrees would get you in the exact same position as if you just went 60 degrees the other direction. So if I had instead moved this way around the circle, I would have gotten to the exact same position, and that's because negative 300 degrees and positive 60 degrees are what are called coterminal angles, because they are angles in standard position with the same terminal side. And an example that we just mentioned there was the negative 300 and the 60 degrees positive. Just continue to go around the circle as many times as we want. There are actually infinitely many coterminal angles for any given angle. To find the measure of a coterminal angle with some angle theta, all you have to do is add or subtract integer multiples of 360 degrees, because going 360 degrees around will put you right back in the same position that you started in. And so in general, to find coterminal angles, we just take the angle theta and we add or subtract 360 degrees times n, where n is some integer value. So say, for instance, I wanted to find a positive and a negative angle that's coterminal with, say, example A, 65 degrees. Well, I could take 65 degrees and I could subtract 360 degrees, and that would give me negative 295 degrees. And I could also take 65 and add 360 degrees, and that would give me a positive coterminal angle of 425 degrees. So those are just, there's infinitely many of them, but those are the ones that would be closest to 65. One is going 360 degrees in the negative direction, and one 360 degrees in a positive direction. But you really could add any integer multiple of 360 or subtract any integer. So I could add like 720 or subtract 720. So any of those would work. So let's take a look at one more, and then I'll have you do some U-tries. So example B, I have 410 degrees. Now if I wanted to get a negative coterminal angle, it's not going to be good enough to just subtract one 360 degrees, because I wouldn't have a negative angle. So instead, I'm going to subtract 360 times 2, or 720 degrees, because that's a multiple of 360. And that turns out to be negative 310 degrees. And then there's really two ways I could go to find a close positive coterminal angle. I could simply actually subtract 360 degrees, because if I subtracted 360 degrees, that would give me 50 degrees. Now that is a positive coterminal angle, so I could do that. But I'm going to go ahead and just add 360 degrees, and that's going to give me 770 degrees. So that would be a positive coterminal angle and a negative coterminal angle. So I want you to go ahead and try a couple more of these. You can pick. Maybe you want to try all three. I'll put the answers down for all three, or you can try a couple until you feel comfortable with finding coterminal angles. Find one positive and one negative coterminal angle for each of the given angles. So go ahead and pause the video now and try a couple of the examples C, D, and E. Okay, so check out whatever ones you tried. And remember, these are simply examples. There are many, 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 infinitely many, as a matter of fact, possible coterminal angles. You can just add other multiples of 360. So let's go ahead and turn the page. So in learning goals, we mentioned something about a reference angle. Well, for an angle theta in standard position, the reference angle is the positive acute angle formed by the terminal side of theta and the x-axis. And so basically we take the terminal side and we just go the closest direction to the x-axis, and whatever measure of that angle is, that's the reference angle. And so because if we're going the closest direction to the x-axis, our reference angle will always be an angle that is an acute angle. So it's like we're kind of referencing angles that could actually be in a right triangle. So again, your reference angle will always be an acute angle. Now, since we always are thinking about these angles of rotation in the coordinate plane, I just kind of fixed up example A and B a little bit to, looks like just the x-axis was drawn, but I drew in the y-axis as well, and you may want to do that. And so that way it looks like, this is actually a angle of rotation in the coordinate plane. So if I looked at this angle here, this angle of rotation, which is 135 degrees, and I wanted to know the reference angle. The reference angle is going to be this angle that's formed right here going closest direction to the x-axis. It's going to be this little piece right in here. Well, because that angle of rotation and this reference angle make a linear pair, the reference angle actually is the supplement to the angle of rotation. So it's going to be found by taking 180 degrees and just subtracting the angle of rotation, which was 135 degrees. And so the reference angle is 45 degrees because that terminal side is 45 degrees away from the x-axis. And that's what we mean by a reference angle. How many degrees is the terminal side away from the x-axis? So with that same thing in mind, for this example B, this would be our reference angle. We're trying to find the angle that is the closest angle to made with the x-axis. So I know that to get back to the x-axis, I'm going to have to travel 75 degrees. And now even though I'm actually having to travel in the negative direction, that clockwise direction we consider negative, reference angles, as I said, are always acute angles. And so it's always got to be between 0 and 90 degrees. So this reference angle would be 75 degrees. So if we want to find a reference angle for an angle that we don't have graphed, what we might want to do is start off by actually graphing it. So we want to go ahead and create a little coordinate plane. And we want to draw our initial side on the x-axis and then graph this angle. So if it's 325 degrees, I have to go, there's 90, there's 180, there's 270, which means I have to go 55 more degrees, maybe somewhere right around in there. And so I've gone a total of 325 degrees this way. And so if I've gone 325 degrees, then the number of degrees left I have to go to get back to the x-axis is represented by that little piece of the graph right there. So I know in order to find that angle, I'm going to have to think about how many more degrees I have to rotate to get to 360. So I can kind of think about it like this, like 360 minus 325, and that'll tell me how many more degrees I have to go, and that's 35 degrees. So I need to go 35 more degrees, so the reference angle right here is 35 degrees. So go ahead and pause the video and give example D a try. Remember to graph the angle of rotation first, and then your reference angle will be the number of degrees that you have to go to get back to the x-axis. So pause the video now. Okay, so that reference angle was 65 degrees. I needed to go 65 more degrees right in here to get back to the x-axis. So the reference angle is 65 degrees. So in the last lesson, we spent a lot of time talking about the special angles, 30, 45, and 60 degrees. Well, it's really important to know the major angles around the origin in the coordinate plane that are multiples of 30 and 45 degrees. And notice I didn't say 60, and that's because 60 actually is a multiple of 30 degrees. So those would all be accounted for if we did multiples of 30. So if you think about the multiples of 30 degrees, and if you kind of just started drawing them in on this circle here, you'd have 30 degrees, and then you'd have 60 degrees, and then you go another 30 degrees, you'd be at 90 degrees. And so these are the first multiples of 30 degrees. We have the 30, the 60 degrees, and then up here at 90 degrees. So then let's say we went and we did another 30 degrees, about there, and then another 30 degrees. And if we did one more 30 degree rotation, we would actually be on back on the x-axis, but going in the negative direction. And we can continue drawing and going another 30 degrees. So if we went another 30 degrees after the x-axis, we'd maybe be about here. Another 30 degrees would put us right about, oops, right about, say, there. Another 30 degrees, and we would be now down on the y-axis pointing down. And then another 30 degrees right about here. Another 30 degrees here. And then by the time we rotate another 30 degrees, we would be right back on the x-axis. So these multiples of 30 degrees would be the 30, the 60, the 90. The next one would be 120 degrees, then 150 degrees, which is 30 times 5. And then another 30 degrees would be 180 degrees. Another 30 would be 210. Another 240. Another 30 degrees added on would put us at 270 degrees. Then 300. Then 330. And then finally we would get back to the x-axis, and this one would be 360 degrees. Now if we wanted to find the multiples of 45 degrees, and we just looked at the first quadrant, so if we just looked at this quadrant right here, 45 degrees would cut that quadrant exactly in half. And so we could just split right down the center here, and that would be at 45 degrees. 45 degrees. If we went another 45 degrees, we would actually be up here at 90. So that one's already been listed because it was also a multiple of 30. So then if we went another 45 degrees past 90 degrees, it would split the second quadrant in half. And that would actually be at 135 degrees. We went another 45 degrees, now we would be up to 180. We'd be back on the x-axis. If we went another 45, we would split the third quadrant down the middle. Oops, and that looks like that's where I better fix where the 30 was. So if we added 45 to 180, we would be at 225. At another 45 degrees, we're down there at 270. And then rotate another 45 degrees, we'd split this fourth quadrant. And so if we added 45 degrees to 270, that would take us to 315 degrees. And then another 45 degrees would take us right back to 360. So basically we were able to get those markers where the multiples of 30s were by taking each quadrant and cutting it into thirds. And we were able to get the place where those multiples of 45 degrees were at by cutting each quadrant into halves. And it's really important to know these major angles around the circle. And later on, we'll start to call this the unit circle. And we'll explain more about that later. But knowing these key values is a really important skill. So let's go ahead and turn the page. So our last learning goal was to be able to determine the value of the trig functions for an angle in standard position. So we know the trig ratios, the SO, CA, TOA, sine, cosine, and tangent, and even those newer trig ratios we learned, the cosecant, secant, and cotangent. But we know them as ratios of sides in a right triangle. But if we are talking about in the coordinate plane and we're just looking at an angle of rotation, well, how does that work? How do we do that? And I think the best way to find out how to find the trig ratios in the coordinate plane is to just look at an example first. So here we have an example, and it says that there's some point P at -6, 9, and it is a point on the terminal side of an angle called theta in standard position. And then they want us to find the exact values of the 6 trigonometric functions. So here's what we'd have to do that. Let's first plot this point at -6, 9. So we're going to count -6 and then up 9, and of course it's not going to fit on the graph. So we'll have to go up one more. So you're right about there. And so this is -6, 9. Now, if that point is on the terminal side, that means that terminal side connects to the origin, and that the initial side is actually on the x-axis. So if I connected that point to the origin, and then I drew in the initial side on the x-axis, that's what that angle of rotation would look like. It would start on the x-axis, and then it would rotate one direction or the other, this way, and it would end up right here. Now, since we kind of only know how to calculate trig ratios in a right triangle, what we could do is we could actually take this terminal side and create a right triangle by using this terminal side as like the hypotenuse of the right triangle and creating the rest of the right triangle with the x-axis. So this is what that would look like. I would just draw in a horizontal and a vertical segment that would create a right triangle with the x-axis. Now, if I knew the sides of this right triangle, I could figure out the trig ratios that were associated with that, that point and that terminal side. Well, you know, these are vertical and horizontal segments in the coordinate plane. Of course, I can figure out the lengths of those. And since, you know, the terminal side here is, right here, is a hypotenuse, well, I know how to find the hypotenuse in a right triangle if I know the two legs. So the two legs are actually going to be just the lengths of those segments. So if I just looked at how far I had to go from the origin to get to this point at -6, I'd have to go 6 units. So that length is 6. And then how many units I'd have to go up to get to that point, since I had to go up to +9, then this side of the triangle is 9. And then I can very easily find the hypotenuse just by using Pythagorean's theorem, which says leg squared plus leg squared equals hypotenuse squared. So I could take 9 squared plus 6 squared, and that's going to equal, and c squared, we usually call this r, though, for whatever reason, we call that r, and so it equals r squared. And so when we square 9, we get 81, square 6, we get 36, add those together, we get 117, and so then to find out what r is, we'd have to take the square root. Well, it turns out that 117 is not a very nice number to have to take the square root of, and there are no perfect square factors, and so we can just express r as the square root of 117. And now we can find all the trig ratios. So we could find the sine, the cosine, the tangent. And when we talk about the sine of the angle, theta, this is the angle we're talking about. We're talking about the angle that is formed with the x-axis. So we're talking about that angle right here. That's the reference angle. That's the angle that is formed with the x-axis. And so to find the sine, well, the sine is just going to simply be the side opposite, which is the side that's 9, over the hypotenuse, which was the square root of 117. And of course, we'd want to rationalize that. We could do that by multiplying the top and the bottom by the square root of 117, and that would give us 9 square root of 117 over 117. Well, that's not a pretty sign, but it is the sign. That's it. The cosine would be the adjacent leg, which is the 6, over the hypotenuse, which was the square root of 117. And again, we would have to rationalize that, so we're just going to multiply the top and the bottom by that square root of 117 to rationalize, and that ends up being 6 square root of 117 over 117, and that's my cosine ratio. Well, the tangent ratio will be much easier because my two legs were both integers, and so the opposite leg is 9, and the adjacent leg is 6, and so if I reduce those, that turns out to be 3/2. Now, when we calculate, you know, these trig ratios, we actually have to keep in mind that this point was in the second quadrant where the x-coordinate was negative. I actually had to go to the left, which is considered to be negative. Now, we don't usually call sides of triangles negative numbers, but technically this was a -6. And what that does then is it makes any of these trig ratios involving that side be negative values. So that cosine actually should have been -6 square root of 117 over 117, because even though a side of a triangle can't really be a negative, because I had to go in the direction of the left to get to that point, that 6 is really negative, which would also make the tangent negative. So that -6, when it reduces to the -2, would make my tangent -3/2. So here when I'm in this second quadrant of the coordinate plane, the sine ratio was the one that was positive. The cosine and the tangent turned out to be negative because both of those ratios used the adjacent side, which turned out to be a -6. Now, to get those three other trig ratios, remember, we can just use the reciprocals. So if we wanted to find the cosecant, the CSC, in other words, of theta, remember that one's the reciprocal of the sine. So if I just took the sine ratio before I had rationalized it, which was 9 over the square root of 117, and I flipped it, I would actually get the square root of 117 over 9. And so I want to take it before I rationalized it, because since I'm flipping it, when I flip that, it takes the radical to the numerator, so now I don't have to rationalize it. And so that's my cosecant. My secant would be the reciprocal of the cosine. So before I simplified it, the cosine was -6 over the square root of 117. So if I flip that, that's just 117, actually the square root of 117 over -6. And so that would be my secant. And I don't have to rationalize that. And then the tangent, I could just simply flip that to get the cotangent. And the cotangent then would be a -2/3. So notice when my triangle, when my terminal side is in the second quadrant, the only trig ratios that give us a positive value are the sine and its reciprocal, the cosecant. So we're going to learn a lot more about reference angles, the coordinate plane, and these quadrants and the trig ratios in those different quadrants in a future lesson. But for today, that is the end of our lesson. So I'll see you in class.